Hello, I'm Professor Paul Bingham, and this is Biochemistry 1. Our goal in this segment is to take the first steps toward mastery of the second half of glycolysis. So this is the second of two lectures on glycolysis. Let me put glycolysis in a larger context for you for a moment. First, remember the fundamental thing that vehicles, organisms do. They build tools to assist in their ultimate replication of the design information that builds those tools. But among the most common kind of tools built are molecular machines that act as catalysts. And one of the most important things that those catalysts do in turn is to flux, a subset of them, is to flux the large amount of energy-rich compounds through our bodies, consisting of the food that we eat, that are necessary to both sustain the activities that we do and also to repair to make spare parts, to repair worn out molecules and ultimately even cells and pieces of tissue. And this fluxing of small molecules continuously through our bodies to generate the energy and the building blocks to build the spare parts that we need is collectively referred to as metabolism. And in the last couple of segments and in the next couple of segments, we're going to be looking at metabolism. Remember the fundamental thing that this fluxing of small molecules through our bodies does from the point of view of generation of energy. We take in reduced hydrocarbons, very much like the gasoline that our cars use, and we excrete the oxidized forms of those molecules. The reduced forms contain a lot of chemical energy. The highly oxidized forms contain relatively little chemical energy. So in the same way that your car burns gasoline to produce CO2 and water, you burn food to produce CO2 and water to sustain your energy requirements. So glycolysis is at the core of the major pathway for the degradation of glucose, the blood glucose, the primary energy source that your cells actually use as a practical matter, and also other compounds feed into this metabolic pathway, ultimately derived from fatty acids and other things, as we'll see later, to also degrade those polymers. But we're going to be focused here on the glucose degradation, or monosaccharide, as you'll see in a few minutes, glucose degradation through glycolysis. Glycolysis goes on in the cytosol, the cell. Later steps beyond glycolysis are going to go into the mitochondria, and we'll have something more to say about that in later segments. All right. So again, this is the larger core metabolic pathways that where almost all of the metabolic pathways either emerge from these or feed into these, as we'll see later. This is the central core of the metabolism that's going on in every cell in your body as we speak. And glycolysis in particular, you'll recall we could break it conveniently, intellectually, and mechanistically into two halves. The first half generates glyceraldehyde 3-phosphate, abbreviated GAP here, which then feeds the second half, which then degrades GAP all the way through to pyruvate, producing the ultimate outputs. And remember the logic of this. The first half, which we talked about in the prior segment, 2 ATPs are invested to produce the the 3-carbon phosphorylated compounds, DHAP and GAP at the bottom of the first half of glycolysis. And then GAP is diverted into the second half to recover a total of 4 ATPs, 2 from each of the 2 3-carbon compounds, to give the whole overall process a net yield, a net profit of 2 ATPs. So let's now continue our journey by looking at the chemical reactions in the second half of glycolysis. And just as you did with the first half of glycolysis, notice the fundamental chemical simplicity of what we're doing here. We're not talking about esoteric reactions that happen to involve small molecules. We're talking about the central flow of matter and energy through your body all the time. This is how it works. This is the pathway through which it goes. Very small molecules, most of them having fewer atoms than you have fingers and toes. And trillions of these molecules are fluxing through your body every day in the process of feeding the energy that you need, creating the energy that you need to function. Okay, so this is the beginning of the second half, the payoff half of glycolysis. And let's look at the first reaction, glyceraldehyde 3-phosphate dehydrogenase, GAPDH for short. And let's look first at the reaction that's involved. Notice the cofactor that's involved here, the other actor. There are 2 of them, actually. There's an inorganic phosphate, abbreviated PI, and there's an oxidized version of nicotinamide adenine dinucleotide. This is a redox cofactor that we haven't talked a lot about yet, but we're going to talk about a great deal more shortly in a couple of ensuing segments. That has the function of receiving and giving up reducing potential in the process of metabolism. So both of those cofactors are involved here. Notice what happens. You're going to create you're going to add an extra phosphate to glyceraldehyde 3-phosphate to create 1,3-bis phosphate, and at the same time you're going to reduce NAD. This is an oxidation event. So remember what we said at the outset, that the overall flow of metabolism is to start from reduced hydrocarbons and oxidize them to oxidized byproducts, and ultimately CO2 and water. This is one of those oxidation steps. So unlike with gasoline in your car where we explosively oxidize it all in one instantaneous process, here we're going to string out the oxidation in a highly controlled way so that we can extract the maximum amount of energy from that process. Well, that is how biochemistry is organized. All right, so this is the enzymatic mechanism of GAPDH. It has some interesting lessons to teach us, some interesting new insights into how catalysis works. So let's zero in on that. So the first step is the loading of the substrate, but let me call your attention to something here, a couple of things. Notice that we're just focusing on the carbonyl compound of the substrate. The rest of the glyceraldehyde 3-phosphate molecule is being symbolized just as R here to keep our diagram simple. But let me focus your attention to the immediate environment and the active site of the enzyme. First of all, the oxidized cofactor NAD has been bound by the enzyme. It reversibly binds to the enzyme, and it's settled in there now in the oxidized form. Notice also that there is a sulfhydryl group projecting out. What is that? That is a cysteine side chain, as I'm sure you know. And then notice the basic group at the bottom acting to carry out, to abstract a proton from that sulfhydryl group, making the sulfur, the residual sulfur, aggressively nucleophilic. What does it do? It then attacks the electrophilic carbon in the substrate, in the next step, producing a thiohemiacetal. That thiohemiacetal is then immediately oxidized by the bound NAD. Notice that NAD has now been converted to reduced NAD, and this thiohemiacetal has now been oxidized to a thioester. We haven't spoken about them yet, but we will later. Thioesters are relatively high energy compounds. There's quite a lot of energy stored in that thioester bond to be given up. In this case, it's going to be exchanged to form a phosphate anhydride with the now carboxylic acid group, the product of the oxidation of the original aldehyde group on glyceraldehyde 3-phosphate. So let's look at that. That is the next step in the reaction. Phosphate is bound, and the nucleophilic oxygen carries out a nucleophilic attack on the very electrophilic carbon, in this case, of the thioester. Notice that carbon is bound both to an oxygen, which is more electronegative than carbon, and to sulfur, which is also more electronegative than carbon. So that particular carbon compound is quite electrophilic. The nucleophilic attack of the phosphate oxygen is a very favored reaction under these conditions. The reduced NAD is exchanged, and the now phosphate anhydride is formed. So notice what we've done here. We've exchanged a thioester high energy bond for a phosphate anhydride high energy bond, and then thereby completing the process. So notice what we've done here. Notice the overall impact of this. Covalent catalysis has been involved. Acid-basis catalysis has been involved. A high-energy thioester linkage has been exchanged for a high-energy phosphate anhydride linkage. Okay. So that's the first step, GAPDH, producing 1,3-bis phosphoglycerate and glyceraldehyde, producing this anhydride as a result of both the oxidation of the